All right, welcome back. Um, okay, I think we're in a good spot here. I have in recording these lectures over and over again, I've learned I am highly reproducible in my lecture timing. I seem to always be within like a slide or two of, where did I finish the third hour last year? Anyway, um, okay, we are here. We have extracted the data from the place that we found it, which we presumably don't like if we're engaging in an extract transform load process. Or we either don't like the place it came from, we don't like the exact format it's in, we want to fix it, and then we want to put it in a good spot. You could do that as a CSV or JSON file. Like that's totally reasonable. It's effectively what you're doing again in exercise 1. Because these are friendly. Everybody understands CSV and like new line delimited JSON. They are relatively slow because of course the text has to be parsed into a data structure of whatever kind. They don't have like date formats natively, or they don't have, I don't know, complex numbers or like whatever. So we can do better. There's things for that. Maybe the place you want to load, and like the verb load makes maybe more sense in the context of a database. I am going to load this data into my database. Fine. Again, we're not going to in this course, but what the hell? But there's these formats that are kind of designed for effectively data frames. Like the kind of thing you think of as a data frame is what HDF5 and Parquet are good at. The Parquet is data format designed for efficient. Yeah, again, efficient storage and retrieval. This is what I probably care about at this point. High performance and compression and stuff. Yeah, awesome. I tend to use Parquet. It's the one I know, like the big data tools support it. And by the way, Parquet, the same, it's the, like a basketball court is Parquet, the strips of wood. This is strips of data. It's not parquet, please. You can do it in pandas. I guess one of the nice things about Parquet is like we know like the column names and column data types are encoded as part of the file. There's no guessing column names. There's no guessing file types. You can override the column names if you want and when we're reading it here. And also it is usually by default, and I think the default here as well, when you're saving a Parquet file, it's usually gently compressed, compressed with a really fast compression algorithm, fast enough you'll never notice the compression decompression time. Yeah, like if what you have is like if you have a free choice about what format to store your data in, maybe that. And like that's, I realized it's what my fingers did here, where if I was doing something like this, where it was get the data, like maybe phase 1 here is effectively my ETL, read the stupid data format, throw away the junk I don't need, have a data frame named D1 and do this to it. And then I know this is going to work. Oh, I guess I'm doing it in Spark syntax here, but it would be the same. I would do dot to Parquet or pd dot read Parquet in a pandas context. And I know it'll be fast. I know it will be, not as fast as if the data is already in memory to do that, but probably pretty close, and I'm happy. Then I can move on with my life. Wrong slides. Again, I see people do this, students in this course, people elsewhere, where they have some really annoying, stupid data file, and it takes a long time to read it and parse it into a data structure, and they've written the code to do that, and then on the next line of code, oh wait, I have to add a column, and they do that. They have to run the whole thing again. So, oh, now I want to do this to my data, and run the whole thing again. Separate that into a separate step. Again, maybe it's a different file. Maybe, maybe this is effectively an ETL step. I'm going to, presumably in my story here, scrape data from an API or some web pages, just get it onto the disk, even if it's in bad format. Then ETL to turn it into something more beautiful, then I can actually start working with it. And if it makes you better, it makes you feel better to call that an ETL process, or like it makes you like you want to describe on your resume as like completed an ETL task to blah, 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 fine, whatever. If you don't like the term ETL and you just call it programming, fine by me. All right. We are moving on. There's my pipeline. This is why I have this link here. We're moving here. So again, the ETL can kind of edge into cleaning up the data a little bit so it's more useful. Maybe not. Maybe ETL spans those two, but I'm now going to look pretty firmly in this data cleaning step. Conceptually, these slides on noise filtering are part of data cleaning, which is the next slide deck that is not revealed as I record this. This is just straight procedural, right? This is, I want to use it in exercise and or whatever, and I'm not convinced I'm going to be done all of data cleaning by then, so we'll pull it forward. Okay. When I'm talking about noise filtering here, this is noise in the like, I guess, yeah, the signal processing sense, where it's just, it's the difference between the truth and the measured value. There's other ways noise can exist, but this is like the sensor or just noise on the wire or whatever. That's inevitable in your data, depending on what you're imagining here. You've got it. Now, how do you deal with it? I made you do this in exercise 1, where you created beautiful data, this absolutely beautiful sign on the input data, whatever the input data was, and then I had you add random normal noise to it, and we called it measurements. And yeah, that's kind of what this is. What I care about is the signal. What I get is the measurement that has noise added to it. And maybe I know how much noise because I calculated artificially. Maybe I know how much noise just because I kind of understand the sensor and everything else. Maybe I just have to guess. But I get that. I want that. What I really want to do is say like measurements minus noise equals signal, but I can't do that. But let's say we have this. So again, this is something like what you had in exercise 1 or / will have in exercise 1. I have done something similar here. I did it without looking at exercise 1, so this is certainly in no way solutions. I think I know what the truth is here, right? Like I think there's a very beautiful sine curve underneath this noise. How do I get that out? And this is a whole like signal processing course you can take in engineering. There's a lot more to be said about it than I am going to say in this course, but I think like noise filtering is a useful technique. And I guess I will say, like, this is not, nobody else's data science course has a noise filtering slide deck. But there have been times in my life, like looking back, I wished I knew some of these techniques way back when. I would have done a better job dealing with that data at the time, because it turns out there's techniques to get noise out of data, not just sort of randomly hoping for the best. What you may not do when doing a noise filtering exercise is ask me, is this smooth enough? That's not the problem here. If you want a smooth line drawn across your data, whatever, I can draw smooth lines across data all day. Not the point. I want the truth. I want the true underlying values that were there, before the noise existed, or, in some magical land where the sensor is perfect and there's no noise or whatever. That's what I care about. I don't care about smoothness of a line on a plot. Totally. Now, looking at a plot and looking at the smoothness of the line might inform you. It might give you a good hint about what's going on, but this is not the goal. Having said that, let's talk about a curve smoothing technique. Because again, like removing the noise is going to often look a lot like making the line smoother. So lowest smoothing, depending whether you want the W there or not, but locally weighted scatterplot smoothing, which is a great term if you already know what it means. Here's the game. So we have our data, and here's my data. Boy, there's some way to change the aspect ratio on a plot. Please hold. Okay, I got it. You know that feeling when you're trying to solve a problem and the link is purple? Anyway, sorry, it's made the plot fit a little bit better. By the way, if you have any feelings about the font size, in the comments, feel free. Okay, I have this data here. Again, I did what I did. Who knows? So I want to get the actual curve out of this somehow, and that's where we're at. What I'm going to do for Lois is take a little window, like a little stretch of the data. So I'm going to, let's say if I look at like between the X 20 and 40, or I guess points 20 and 40, there's 100 dots here somewhere. So if I look at just those, okay, just that window on the data, do a linear fit, like just do the basic least squares. Oh, but maybe not the basic least squares. I'm going to weight the things towards the middle of the range higher. That's more important to what's going on here than the stuff out in the edges. And then I'm going to say, there, that's what I've done. I'm going to draw a dot. And then I'm going to move over a little bit and draw another dot. Move over a little bit and draw another dot. Or this. So in this animation, the 4 panes are a different size window, like how big a fraction of the data. So if I only look at a quarter of the data at a time, I will do this, and I'll have these linear fits go across as I go, and I'll just draw a dot at the middle of that linear fit each time and connect the dots. So if I have too small a fraction, I'm going to sort of follow the noise around a little bit too much. If I have too large a fraction, I'm missing real things that are happening in the data. Have I talked for long enough while this, fundamentally my goal here is let this animation run. So again, if I only have one choice to make here, and it's how big is the fraction. Small fractions don't smooth as much, large fractions smooth more, and maybe too much. And thank you to David Robinson for this thing that I've found way back when. Where's the, okay, well, that's the thing I stole. Yeah, this is maybe a better just animation of doing it once. Where again, how dark the dots are is how important are they to the decision of where this line goes? How much are they weighted in the sum of minimized sum of squares calculation? And then as we go, we look at different parts of the data. The line, the best fit line changes, and we move across and draw that line. That's the output of this lowest smoothing process. Yeah, we have one choice, and it's the fraction. How big a neighborhood? Small numbers, closer to the original data. Large numbers, smoother. You want both, right? Like you want both close to the data and smooth, and you have to trade that off. There's no rule here. I do kind of wish that animation had a smaller fraction example where you really did get this. And yeah, if this fraction's small enough, you're just chasing around the noise. If the fraction's too big, you're losing reality. You need to play around and get somewhere in the middle. If you have a nice big dense data set, lowest smoothing is probably the way to go. It's super easy to work with. If I don't have much data, it can get rough. So this, I think I forced you to do this in exercise 1, so you've seen this at least a little bit. There's a thing for this, and it's just a matter of doing that. Okay, so I am looking at this, and I don't have an input range here. Um, see, this is, well, it's both what I get for not preparing carefully and why I don't prepare carefully. I wanted to show this. This is how life works sometimes. All right, and then wait, no, I want both on the same plot. So I want this. That's stuff. What is it? Wait. I know it's in my slides. Like I know for a fact this is in my slides. But right, what this gives me is not actually just the filtered data. It gives me the x values and the filtered y values as two separate columns, right? So what I want is only the second column of this. So I want all rows, column 1, right? That feels right. There we go. And then, of course, we delete this because we pretend we knew what we were doing all along. And come back here. Yes, these parameters are in unambiguously to me the wrong order. These are the x values first. Oh, sorry, the x values second, the y values first. I can't even say it. And I guess, okay, I didn't include the x range in my plot there. I did here. So when you hand matplotlib just data points, it just counts them. So this is data point 20, data point 40. I do have x, I have real x values here, so I might as well use them. Yeah, okay. And now I think about this. I think, have I smoothed it in a way that I think I'm getting the truth, or too much or too little? That's not exactly the same thing as removing the noise, but it's often very similar to removing the noise, and it's really easy to do. So I probably look at this and I think I'm not smoothing enough. I'm still capturing noise here because I have a very small fraction. And yeah, just by chance, because randomness works that way, I have a couple of points in a row here that are too high. So if I only look at those, my output line is too high or too low or whatever. So I probably want a bigger fraction here. 0.2. That's probably pretty good. If I have too large a fraction, yeah. This fraction is too large. I'm over smooth. I have a beautiful smooth line. This line is definitely smooth, and it also does a really crappy job representing the truth. So this output line, no, I liked point. Well, again, I could try a few more. Usually there's a pretty wide range. Right? I might argue that this is a little worse. I think I'm, off on the edges here. I don't have enough data to kind of capture this thing that I think is happening. Actually, I did like 0.2. Again, some people will look at this and think, oh, but it's still a little bumpy. Well, maybe the truth is bumpy, right? Like here, and often in the lecture examples in this course, I'm cheating, right? Like I'm cheating by knowing the truth. I don't usually get to know that. Usually I have to look at this and I think, well, what do I think the truth is? And I have to make a judgment call about whether I've done a good enough job capturing it here, or if I have to experiment a little more. I think I'm okay with that. Yeah, sure, why not? Something I did say back there was like, yeah, if you have a lot of data, it's better. If you don't have much data, well, what am I going to do here? Here, my fraction is big enough. Like, I'm just playing connect the dots, right? Like, fine. That's not so bad. Geez, that's not bad. That is okay. But with really sparse data sets like this, if you don't, and again, it just depends where your data comes from. Sometimes you have data that is just, again, you have data, and I have a reading every second and I'm trying to look at data over the scale of weeks, and this is just too much. Well, these things can be that in that case, yes, lowest filter, it's fine, no problem. But if you have kind of sparse data, you can get yourself into trouble. Maybe you have to be a little bit more careful, a little more manual. Okay. And again, please keep this in mind. The difference between finding the true underlying signal and removing the noise. In practice, what you're doing most of the time is trying to smooth the curve. But yeah, just keep in mind, this is the goal. But let's talk about another technique. So hopefully you're in a situation where you know more than just the line is bumpy when I plot it. Right, like if you're back here, you would look at that and say, oh, this isn't right, right? If I treated this like this is not the truth, I'm pretty sure. I would like to smooth things out, and fine. But maybe I know more about what's going on than just bumpy line. And a Kalman filter is going to get us there, and it's got a lot more to do. There's a lot more to sort of parameterize and to think about in order to get a Kalman filter to work. But it's really, really good at it if you can get all of that right. If you can parameterize everything right, it's magic. It's a maximum likelihood estimator. So there's going to be a bunch of probability in the next things I say. And what we're doing is what the Kalman filter is doing for us is looking at this probability distribution that we're going to sort of infer from the data and what we know about the data and the process and where it comes from. And then choose the most likely, choose the highest probability, that's the output. So hopefully I know, or I can infer or guess or make a good guess about these things. I know how much error there is in my sensor, my measurements, or whatever. I maybe know something about how the thing actually changes. I might know, it's accelerating this much, or I expect no more than this much change per minute, or something like that. I'd better know how to make some kind of prediction about what happens next. So if I know the acceleration, I can probably make a pretty good guess about where things are going to be in the next time step. I have to know some stuff for that. I have to know how the system works, but maybe I know how good a prediction I'm making. Am I making a really good prediction or a really bad prediction? If I know a bunch of that stuff, Kalman filter. Okay, let's do a little review here. Probability distributions exist. They exist in the abstract, right? Like we don't know probability distributions. We infer them from data sometimes, or we know them because we know how things work. Probability distributions have a mean. That's that thing you can, well, if you know the probability distribution, the mean is just a property of it. So is the standard deviation or the variance. The standard deviation is how far are things spread out around the mean. And then when you're measuring something, you're sampling from this distribution. In reality, I never, like in math class or stats class, I know what the probability distribution is. In reality, I never know this. I know what the data is, and I could guess the mean and standard deviation of the probability distribution, but it's only a guess. It's inferred from the data. What we are assuming here is Gaussian noise unbiased. So, there's a normal distribution. Hopefully we've seen a normal distribution before, the thing that has this probability density function, where there is, and I guess the assumption we're making here is that the noise is sampled from a normal distribution around the truth. So again, if we knew this distribution, then we would know, oh, right at the center, that's the truth. That's the true underlying value, but we don't get that. What we get are measurements that are sampled from this probability distribution, and we're hoping to infer what that mean is. Um, if that measurement is not centered around the truth, we have bias in our sensor. Like this is just like the thermometer always reads a little bit too high, and we can't fix that here. You can fix it by just subtracting from the number, but it's not a noise filtering problem. It can happen, right? Like you definitely have this. Like I have a clock in the next room that's just 3 minutes fast. I know I could fix it, but I just wake up and look at it and no, it's 3 minutes before that. Great. So we have this kind of thing. And again, the picture for the sort of telling of the story for the Kalman filter is the truth is 0 in this diagram. The absolute truth of what this value is, that if we could measure it perfectly to the nearest atom or whatever, the truth is 0. We don't get to measure it perfectly. What we do is get to sample from this probability distribution. That's what our measurement is. So again, if it's a thermometer or we're measuring with a ruler or whatever it is, that's the story. We measure and we get a sample from this distribution. So maybe sometimes we get, negative 0.8. Okay. Next time we get positive 0.8, who knows? What I do know is that if I can know the mean and the standard deviation, I can estimate the mean and standard deviation. I know that about 2/3 of the samples that I will get are 1 standard deviation away from the mean. So I can kind of look at the measurements that I'm taking, and I can know, well, I don't know, but I can guess. I bet the mean is around here, and I bet the standard deviation is about this, because it's basically, well, what do I have to do to draw a band that includes 2/3 of the data? That tells me the mean and standard deviation. Because again, I don't get to know the true distribution. I have to guess from the data. I feel like they should say that more in the stats class. Probability distributions only exist in our heads. They come from, or they're inferred from, measurements. If I have 2 variables, 2 features, 2 things I'm measuring, 2 probability distributions, the covariance is telling me about how related they are. And it's going to come up in Kalman filters. I guess if I have a covariance of 0, what I'm saying is there's no linear relationship between these 2 things. If I have a positive covariance, they both get big at the same time. If I have a negative covariance, when one gets big, I expect the other one to get small, usually. What we're talking about here is noise. So the random variables that I got are expressing the noise on my measurements. So the covariance here is going to mean a positive covariance would be if the error on this measurement is high, I expect the error on the other one to be high as well. Not that the value goes up, but the error goes up and down together or opposite each other. So I've got 2 big categories of thing here. I have my data. I measured stuff. I read a CSV file, whatever it is. And then we are going to make a prediction about what happens 1 step in the future. We'll talk about how that gets done. And if these are the same, well, then probably I'm happy, but they're not going to be, right? There's going to be some kind of disagreement between these 2, and there's going to be some error on each one. I think my observation has random normal noise, which again, that's just an assumption. It's often pretty close to true. And I'm going to assume my prediction is also, the error in my prediction is also normally distributed. Kalman filter is going to smash those 2 together. And actually, I just described a probability distribution without saying it, right? If I have observations that are drawn from a probability distribution centered on the truth with standard deviation, whatever the error is, and I have a prediction that I hope is centered on the truth and has an error, well, then I've just described a probability distribution for each one. We're going to put those together and choose the most likely result. Or in probability density function speak, this. So I am measuring, and I've just decided that I know, oh, sorry, I have measured 5. Um, Again, I got out my ruler, I got out my thermometer, I got out my accelerometer, whatever it is. 5 came out. I think the error on my sensor is around 2. So that is, again, this probability distribution has standard deviation 2. That's what I sort of say in the notation on the slide. What I think when I say that is 2/3 of the time, my sensor is going to be within 2 units of the truth. So I have this, again, 1 standard deviation away from the mean on either side will contain 2/3 of the area under this curve. Do I think my sensor is usually within 2 units of the truth? Well, if it's a thermometer, does my thermometer usually read within 2 degrees Celsius of the truth? Probably. I'm probably pretty comfortable with that. I have to know something about my sensor. And then we're going to make a prediction, again, which we don't know how that prediction is being made, but there will be a prediction. The prediction in this story is 8. Again, I've done whatever math produces a prediction. It's 8. I'm a little less confident in my prediction than I am in my measurement. I'm going to say my prediction is usually within 5 units of the truth. So the measurement that I just took it tells me that the truth is drawn from this blue distribution. The prediction I just made is telling me the truth is drawn from this red distribution. I want to know what the truth is, or I want to make a best guess of what the truth is based on those 2 things. The thing is the product. The product of 2 probability distributions is if there's one value that's drawn from both of these distributions simultaneously, this is that distribution, that sort of combined distribution. There's a formula for it. If you're in the normal case, I guess I did it to produce this plot, but it told me this. It told me that the truth, best guess on the truth here is the peak of this distribution, 5.8. That's the game that's being played here with a Kalman filter. So again, I have 2 things. I have my observations and I have some good guess about how wrong they are, expressed as a standard deviation. I have a prediction. I don't yet, but I will have a prediction, and I have some good, hopefully, estimate of how wrong it is, expressed as a standard deviation. The Kalman filter is going to say, oh, okay, you've just told me about 2 probability distributions. I'm going to take the product, take the maximum likelihood, and that's the output. That's my noise filtered output. If you feel like you need notation for all of this, sure. So this is, I guess we have time steps or observations or whatever, like whatever, time unit is here. And there's a truth that we don't know, but we're going to try to estimate. There's our guess about what will happen. So this is, if we know what happened at time k-1, here's a calculation that will produce a prediction for the thing that will happen at time k. It's not a perfect prediction, but it's a prediction that's hopefully okay. And also we have the measurement at time k, put those together and do our best to estimate the output. And I think an example is in order here. Suppose we have a cart, like a robot on a track or something, right? So I only have 1-dimensional position and velocity. But then the world looks like this. It has, like at time k, I have a position, I have a velocity of my little cart. That's everything I know about the universe. Oh, but I do know how to make a prediction with this. If you tell me what things look like at time k-1, if you told me the position and velocity, well, I have a really good guess for the position in the next time step. It's this, because I remember that thing from physics class one time. However long my time step is, velocity times that's how far the thing moves, add that to the old position, that's where we're going to be in the next time step. I don't know, based on at least the story that I've told on this slide, I have no way to guess the velocity in the next time step, but I can make a bad guess, right? I can guess that, well, There's not much friction in my cart, so I'm just going to guess the velocity stays the same. Maybe there's a little friction. Maybe I would say like 0.99 times the velocity in the previous time step, but I've some guess. I guess maybe I have a world where there's a third variable, and the third variable is like the amount of the voltage being applied to the motor. And then if I knew like what was going on with the motor, well, that would probably tell me something about the change in velocity, but I don't have that here. So hopefully you're not mad at me for these two equations, right? Again, they're guesses. I think the position is a better guess than the velocity, but this is not a bad guess about where the robot's going to be one time step from now. Okay, now if I rephrase that as a matrix operation. So again, I have the thing at time k is these two. It's a vector of however many variables I have. I just figured out these formula on the last slide. Again, going from time k minus 1 to time k, that was what I said a slide ago. Again, this is just a column vector of the two things. But it turns, I can express it, as long as I have linear combinations here, I can express that as a matrix multiplication. So this is the state of the world at time k minus 1 times some matrix. If you haven't seen matrix multiplication before, because there's no linear algebra prerequisite to this, Google matrix multiplication. It works like that. Anyway, so now I have my prediction expressed as a matrix multiplication. All I need is this matrix that tells me what prediction I'm making about the thing that will happen a time step from now. I take the matrix, multiply by the thing at the previous time step. That's my prediction for the next time step. That's it. So this thing is called a transition matrix. It's what's my prediction for how we transition from time k minus 1 to times k. I have to express it as a matrix multiplication. A matrix multiplication is pretty flexible. That lets me do any combination of the other variables. And I guess maybe I'll point out here, right? So this, the things that are happening in this matrix are in order, right? My first variable is position. So these are the coefficients of the formula for calculating position. 1 times the old position plus delta t times the old velocity. These are the coefficients for calculating the velocity. 0 times the previous position plus 1 times the previous velocity, which is what I've said there. So each row in the transition matrix is about predicting the corresponding variable, first row, first variable. And then across is what do I multiply that variable by to get the prediction, and add them up. Okay, so I have a transition matrix, or a thing I've just decided to call a transition matrix. It's that. That's the last step. Again, just in case your linear algebra is a little weak, the identity matrix, this thing that is all zeros except ones down the main diagonal, if you go through this process of how matrix multiplication works, this is the one of this world. If I multiply by this, nothing changes. Okay, so if my transition matrix is this, my prediction is the thing in the next time step is the same as the previous time step. That's not a very good prediction, but well, it's a not incredibly stupid prediction. Like, it's not the dumbest thing ever. Like if I filled in all zeros here, if my transition matrix was all zeros, my prediction is the next thing that happens is all the sensors read 0. That's probably bad. This one is encoding everything, the next time step, things stay the same. And in fact, like this row in this transition matrix was in the next time step, everything stays the same. It's the corresponding row from the identity matrix. I did change a little bit in the first row, but second row, I left it as this, which encodes stays the same. Again, as long as you can sort of express yourself with linear combinations of the variables or what makes the prediction, you can come up with this matrix. You know, it's not always the case that everything is a linear combination and that's the best prediction always, but often. Okay, so I have two things here. I have a prediction because I have a prediction matrix, or transition matrix, and I have a measurement because I have a data set. Now I have to figure out, how wrong are they? How wrong is the measurement? How wrong is the prediction? That's part of the story I told back here. If I don't know the how wrong are they, I can't, and I need it as a standard deviation, then I can't draw this picture, so I need it. So these are covariance matrices. You do get a chance to express covariance, which is if you think the error on the sensors are related, you could put a non-zero thing here. I'm not going to. For this class, we're only going to worry about the diagonal. I'm going to put zeros everything everywhere else. They are variances that go in this matrix. I find it way easier to think of a standard deviation because, like, if I'm measuring temperature, the standard deviation is in degrees Celsius, right? I can think about that. I can look at my thermometer and I think, well, it's usually within 2, and I can think the standard deviation is therefore 2. And then I can square it and call that a variance of 4. I can't think about a sensor and think about the variance. I don't square things that fast in my head. So when I've said like 0.001 here, that means that I think this sensor 2/3 of the time reads within 0.001 units of the truth. Whatever the unit is a unit meters or degrees or whatever, well, 0.001 of them, that's how good my sensor is. And yeah, they are not correlated, which is why I put zeros everywhere else. That's the story. And I guess I need this for both. I guess I just described this as if it's for the sensor. I think the sensor for variable 1, or the measurement of variable 1, is usually within 0.1 units of the truth. I do this. Or I also have to tell this whole story for my prediction. I think when I predict variable 1, I usually, 2/3 of the time, predict it within 0.1 unit of the truth. Then I put a 0.1 there. And I square it, and then I say it's the variance. So again, I need it for both. There's one of these matrices for the observations, one for the predictions. If you want to call them bold-faced R and bold-faced Q, that's fine by me. And again, don't try to think about variance. You'll hurt yourself. Think about the standard deviation and then square it. Again, because standard deviations make a huge amount of sense. They're in the unit I'm thinking of. Okay, and I've got just about enough time to start this. Okay, I saved this already. Okay. Now, it's all well and good to tell stories about probability distributions, but I want to actually do the thing. I don't want to do it myself. There's a library for this. PyColman seems like a good one. So same kind of story here. I'm creating this picture of, well, I have like sine and cosine as 2 separate variables. I've added some artificial noise to them because, and by the way, if you like, literally this should generate the figures from the slides because that's all I did. So if you look at this looks bad, right? Like it looks like there's not much left here. I guess I could imagine, if I really thought hard about it, I could imagine a sine curve there. I could imagine a cosine starting at 1, going down to -1, coming back. I could imagine those in there, but there's a lot of stuff gone there. I could try to Loess smooth them, right? We have that tool still, and it does a surprisingly good job. You know what? I'm gonna have different random noise. It's no fun to produce the exact same plot. Don't usually do this, by the way. Like, don't set the random seed. Let your randomness be random. I'm going to do it just so I don't change my plot every single time I rerun this code. And again, I did it on the slides so I could reproduce my slides. This isn't bad. Like, honestly, you know, I had to choose a fraction. I played around a little bit to get ones I liked. You know, if I decrease them a little bit, I'm going to guess, yep, little noise kind of stays in there. If I increase them too much, yeah, I'm kind of over smoothing reality out of it, but this is pretty good. Okay, but let's, in our last few minutes here, get back to the Kalman filter. Okay, so again, there's a lot of parameters for a Kalman filter. I need to express my covariant of my transition matrix, my predictions about what happens in the next time step. I also need, actually, one thing I didn't mention, which is, what do I think happens in the first time step? What do I think, how do I think the world starts? My matrix isn't going to be any good for that. So, how do I know there's a way to split a cell. Is it like control? Nope. There we go, Control Shift. Okay. So I have done this. This is like the only time I ever index out of a data frame. How do I think the world starts? So maybe I know something. I could know something here. In fact, I do know something really good about what sine and cosine look like when you evaluate them at 0. But if I don't, my best guess for how the world starts is whatever the measurement was when the world started. And that's what this is saying, right? So you just take the first row. That's my guess about the truth at the first time, because I don't know anything better. That's actually pretty good. I got relatively little noise there. My observation covariance, this is how much error do I think there is on the measurements. So what I would do really is I would look at this and I would say, okay, I have to kind of eyeball and guess where the truth is here. And what I'm going to do is, like, if I looked here, I would say, okay, the truth is probably here. How wide a band do I have to draw around that before I get 2/3 of the data? That's my guess for the standard deviation. What do I got here? So it looks like it's there. I could use a different scale on my graph, 0.2. And over here, it's, yeah, something like 0.5. So yeah, if I was just doing that by eye, I probably would have come up with those numbers, or maybe, something like that. Here I cheated because I know exactly how much noise is on my sensor because I put it there artificially. And then again, square it and call that the thing. All right, so the np.diag is create a diagonal matrix with these things down the diagonal. And then if I square each value in that matrix, that's exactly what I want. That's the observation covariance. And I'm not done yet, right? I haven't said everything. Everything is going to have to wait. Well, I can do a little bit. Okay. I can do at least this much. I can say I will have a prediction. My prediction is take the thing that happened in the previous time step. And because I remember something about calculus and how to take the derivative of a trig function, this is how I think things are going to change. This is how much error I think there's going to be on my prediction. And when I start to do that well, I start to get really good results out of a Kalman filter. So that is going to be where we stop because we're out of time. See you in the lab on Friday. So you don't need this for exercise 1, certainly. So I do have another lecture to talk about this a little more fully before you need it. Yeah, see you on Friday, and have fun with the exercise.